Our today's topic is coset. In group theory, how we define coset. The definition of coset is, let us consider G be a group with binary composition star. So G be a group with binary composition O. So consider a subset of G, that is H, such that H be a subgroup of G. Then for every A belonging to G, AOH defined as A multiplied by, or whatever the binary composition is, either it is plus or multiplication, we will write it as AH, so that H belongs to capital H. Then AOH is called the left coset of H in G. So I am again repeating what it says. G be a group, H be a subgroup. For every A belonging to G, the elements or all the elements in the set are of, if are of type AOH, then AOH is called the left coset of H in G. If you multiply A from the right hand side, then we call this set a right coset of H. It is a simple definition. It says that if you have a subgroup H, say containing some elements H1, H2, so on, then if you multiply all the elements H1, H2 from the left hand side with some element of G, say A, that is AH1, AH2, so on. So this new set is called left coset. And if you form another set by multiplying or addition, whatever the binary composition is, from the right hand side, that is H1A, H2A, so on, then this is called right coset of H. Now since G is a group and a group satisfies the closure property, A belongs to G, H belongs to H, which is further a subset of G, that means H also belongs to G. So by definition of group, AH also belongs to G. So this new coset you have defined, say AOH or HOA, left coset of H or right coset of H, these are again are subsets of G. So we will call, the definition is AOH containing all the elements of type AH, then this AOH is called left cosets of H in G, and HOA is called right coset of H in G. Let us consider an example. Suppose you have a group G. I defined a group G as a set of integers with the binary composition addition modulo n. Now this Zn we also defined, suppose A be any element of Zn, then we will write A as written in this symbol square brackets equals to A plus Kn, where K belongs to set of integers. For example, if I define Z12, then the elements of Z12 will be 0, 1, 2, 3, so on up to 11. I will write it as 2 belongs to Z12, whereas this square bracket symbol I will use for say 2 plus some k 12, where k belongs to integer. What I meant to say that Z12 contains remainder of an integer whenever it is divided by 12. For example, if we have 13, so 13 square bracket is written as, when 13 is divided by 12, that is 12 plus 1 equal to 1. So we define this Z12 with binary composition addition modulo. Now let us see what will be the cosets of this Z12. If you consider a set Z12, let again write G be a group defined as Z12 with binary composition addition modulo, and say H be any subgroup of G written as 0, 4, 8, then what will be the left cosets of H in G? So if I define a left coset, say 0 plus H, that means I am adding element 0 to all the elements of H. In that case I will get 0, 4, 8. So another left coset 1 plus H, that will come out say 1, 5, 9. Continuing in this manner, we have a coset 4 plus H, that is 4, 8, 12. So 4, 8, 12, but 12 stands for that whenever you divide 12 with 12, the remainder will be 0. So this set is nothing but 4, 8, 0, which is same as the coset 0 plus H. So whenever you will find another cosets, say if you find 5 plus H, then it will come out to be 5, 9, 13, which is further equals to coset 1 plus H. So we can say that these cosets give rise to partitions. So our conclusion is that cosets give rise to partitions of a group. So divide a group in a partition. From this example, we can also conclude that either the cosets will be distinct or they are equal. That means if you will go on defining 6 plus H, 7 plus H, 8 plus H, these cosets again come out to be 1 plus H, 2 plus H, 3 plus H. So our next lemma is based on the conclusion of this example. So our next lemma says that if you defined H a subgroup of finite group G for all element AB belonging to G, then the number of elements in AH will always be equals to number of elements in H. So here AH is the symbol used for left coset of H. If we prove this lemma for left coset, that means it also goes for right cosets. So we are here going to prove that number of elements in left coset is always equals to number of element in right coset, and B, either the two cosets are equal, so AH is the one left coset, BH is another, either AH equals to BH or AH and BH are disjoint sets. That means if you pick any two left cosets of H, they does not contain any common element. Either they will be equal or disjoint. So the proof is very simple. First of all, we prove the A part. Now since AH is the left coset of H in G, that is written as AH equals to A into small h, where this H belongs to subgroup H, or you can write it as AH1, AH2, so on, AHI, AHJ, all the combinations. Now as H is a subgroup, since H is a subgroup, AH belongs to A capital H, so this means this element AH also belongs to H. So that means for every AH in left coset AH, this element also belongs to H. That means that AH is a subset of H. So we can conclude that number of elements in AH are less than equal to number of elements in H. Now if number of elements of AH are less than equal to H, that means we have two elements, say AHI and AHJ, those are equal. AHI is equal to AHJ, but H contains distinct elements, that means HI is not equal to HJ. So AHI equal to AHJ, where HI is not equal to HJ, though then by left cancellation law in group, we have HI equal to HJ, but that is a contradiction. That means no two elements in left coset are equal. That is, there are no two elements such that AHI equals to HJ. So this implies the number of elements in AH are always equals to number of elements in H. Now comes to the B part. For B part, assume that AH and BH are not disjoint. They contain some common element, and that common elements can be, say, C be such common element such that C is also belongs to AH and C also belongs to BH for every H1, H2 belonging to H. Now from here, again applying right cancellation law, we get A equals to BH2 H1 inverse. Now again assume that X be any element of AH. So X will be of type A H type. So this means X equal to AH, where value of A is equals to BH2 H1 inverse H, but H is a subgroup. So by closure property, H2 into H1 inverse into H, it is an element of H. So this means B into H2 H1 inverse H is of type B, say H4, which is again belongs to BH. That means X belongs to BH. So every element of AH every element of AH belongs to BH. So that means AH is a subset of BH. Similarly, we can show that BH is a subset of AH. So if left coset AH and left coset BH both are not disjoint, so we will get that from say this 1 and 2 AH is equals to BH. So any two left cosets will either be disjoint or identical. Either disjoint or identical. So this conclude our lemma. This lemma again plays a very important role to prove Lagrange's theorem. So Lagrange's theorem says that if G be any finite group of order n and H a subgroup of order m, subgroup of G of order m, then m divides n, written as m divides n. It is very important theorem. It also helpful in number theory and has a very interesting proof. So we will start with its proof. Suppose you have a G, a finite group whose order is n, H, a subgroup whose order is m, and we have to prove that m divides n. So we start with assumption. What assumption? Let us suppose that H equal to G. So if H equal to G, then there is nothing to prove. Result follows, and m divides n, that is m equals to n. Otherwise, suppose that m is less than n. The order of H is less than order of G. If order of H is less than order of G, this means there exists some element that belongs to G but does not belong to H. Let us that element be A. Now this element A belongs to G but does not belong to H. It is A belongs to G minus H. Now since A does not belong to H, that means if you find a left coset of H, that is AH, that will not be equal to H, because if A belongs to H, every element AH will be also element of H. But if A does not belong to H, that means every element of AH will not be an element of H. So AH is not equal to H. But previous lemma says that if you have two different cosets of H, then either they are equal or they are disjoint. But here AH is not equal to H. Therefore, by previous lemma, AH intersection H is a null set. So again two cases arise. Case 1, that is if G is equals to AH union H, then this implies number of elements in G, or you can say that order of G equals to number of elements in AH plus number of elements in H. Both are equal. We know that number of elements AH are equal to number of elements of H, that is 2 times number of elements of. So theorem follows. If that case, then theorem follows. But if not, then again there exists some element, say that element B such that B belongs to G, but B does not belong to H or AH. Now we have coset BH and intersection of two cosets will be null set. Either they are equal or they are disjoint. That means BH intersection AH is null set, BH intersection H is null set. And number of elements of BH equals to number of elements AH equal to number of elements H. So in that case, again two cases arises. Case 1, if G equals to BH union AH union H, then what will we have? That number of elements of G equals to 3 times number of elements of H. So theorem follows. But if not, that means there exists an element C such that C belongs to G but does not belongs to BH or AH or H. So continue in this manner. We will see that we comes to a point as G is finite. We comes to a point such that G equals to say A1H union A2H union A3H so on union AKH. That means the number of elements in G equals to K times number of elements in H. So theorem follows, that is M divides N. So this is the Lagrange's theorem. We conclude our lecture here. Thank you all.